Good day. There'll be more lift. If you could all look up there, might see it better if you close the door. I'm just gonna make little screencasts right now to help you. Here's what I see. Your diagrams. A lot of you guys are just looking at the diagram on the worksheet. You don't want to use those diagrams necessarily. Sometimes the diagrams on the worksheets are good. For example, here's what I would draw for plane going. The first one I think is the bottom of the loop, right? Yes. I would draw this. There's my plane. There's a wing. There's another wing. There's the tail wing. There's the side wings. There's the jets. You guys with me? I would do a rear view of the plane. And I would say it's at the bottom of a loop. Okay, is everybody with me so far? The reason I chose this perspective is check out how simple the force diagram is going to be. What do I have? Weight. What else? Okay, I got lift. Do you guys see how I did it wrong? And people noticed. Which way is the acceleration? Up. All right, so I made a mistake, and that's good because it's perfectly normal.
Wait, is it? So the lift is longer than the weight.
Why is the lift longer than the weight? And I think we interrupted Christina. Go.
Is the airplane on the bottom of the circle right now?
Yeah, I wrote bottom of the loop. You're right. So this is what's very promising. If you can actually use the direction of acceleration to correct your force diagram and your vector sum diagram, you're probably going to nail it. You're probably going to get it right.
Wait, if we have lift, do we not put net force?
Okay, now let's add the forces. Are the forces adding to 0?
No, because there's acceleration upward.
All right. So what did I just do? I didn't mean to stop it. I'll write airplane, and I'll call this project airplane. So when it goes on classroom, it'll. There we go. All right. What was your question again? Something about net force, right?
Oh, can we start putting the forces up?
Yeah, but you want to add the forces first, right?
Yeah.
Are we going to get a net force of 0?
No.
And you won't be, whenever there's acceleration, you won't get a net force of 0. So I got lift, and I'll draw my weight shorter. In fact, you knew that the weight had to be shorter because you knew there was acceleration upwards. And then I'll draw my net force up. And hopefully you're doing this check. You're looking at your net force vector, and you're making sure it's in the same direction as your acceleration. And you're looking at your net force vector and making sure it's not head to tail with the vectors you're adding. Then it would be in the wrong direction. Those are common mistakes people make. And then you could label your net force mv squared over r, which is ma, when you're going in a circle with a constant speed, right? And the problem's really simple from here. We get L equals, can y'all help me? mg plus, all I'm looking at is the length of the vectors, right? And you should probably make it look cute. Factor out an m, what do you get?
2m.
G squared over R.
G squared over r.
Are you guys cool? Now let's do the same thing, except we'll do top at the top of the loop. So there will be more. Oh, look at what it's doing. I'll draw my airplane again. There's my airplane. There's my jet engines. And what are the forces acting again? And what's different this time? Which way is my acceleration?
Downward, so your weight.
All right. Downward, so what'd you say again?
Your weight is greater.
All right, so the weight, he said the weight is greater. How'd you know that?
Because if there's acceleration downwards, the only way, since the two forces acting on the plane are lift and weight, and if the acceleration downwards, that means the weight has to be larger for the plane.
You need to hear yourself making beautiful explanations like this. That's how you're going to understand. Go ahead.
This may seem like a stupid question, but
Don't worry.
if a force out, okay, so you see how weight is longer than lift?
Yes.
In that force diagram?
Yeah.
Does that mean that it goes down necessarily because that force is longer?
Does the direction of the net force is down, right?
Yeah.
Does the direction of the net force tell you anything about which way you're moving?
Yes.
No.
Yeah.
Does the net force tell you anything about your velocity? Net force instead is connected through Newton's second law. Net force is connected to acceleration, not velocity.
So just because a vector is longer than the other, that doesn't necessarily mean it's going that direction.
In fact, we don't know the velocity of the plane at this moment. It could be anything. Whenever an object has forces acting on it, and all you know are the forces acting on it, a lot of you missed this on the last quiz. The forces acting don't tell you anything about the velocity, but they tell you everything about the acceleration as long as you know the mass. Does that help? That was a great question.
And when they're equal to each other, like say it formed like an equal T, that doesn't necessarily mean it's stationary.
Another great comment. Did y'all hear it? When the forces add to 0, please be precise about what that means.
That means the acceleration is 0.
If the acceleration is 0, does that tell you anything about your velocity other than the fact that it's not changing?
Yeah.
It doesn't tell you what your velocity is. It doesn't tell you which way you're moving. I'll go ahead and finish this up right now. Please put the chairs up. You don't have to watch or anything because I'll record it and post it. Put the chairs up and have a great day. All right. So for this problem, just to wrap it up, weight down, lift up, and the net force therefore would be down, right? mv squared over r is our net force. So in this case, our lift is mg minus mv squared over r, which means lift is mass g minus mv squared over r. Oh wait, I messed that up. Let me fix that. G minus v squared over r. So you can see less lift at top of loop.